Hi, in the last video, you saw the derivative of natural log function, right? What you saw is the natural log of the derivative of natural log of x is equals to 1 over x, right? So the d over dx is the derivative of ln x, which is the natural log of x, is 1 over x. Since the antiderivative of antiderivative is the inverse of the derivative, that's the opposite, so the antiderivative of that is natural log of x, right? If you take the antiderivative on both sides, then you will get the antiderivative and derivative will cancel out, so they are inverse to each other. So natural log of x equals to the antiderivative of 1 over x, right? So you write integral of 1 over x dx is natural log of absolute value of x, because the natural log is not defined for negative numbers. That's why we write absolute value of x plus c. Okay, so on this example you see that. So what is the integral of 5 over x then? Because if you have 1 over x, then the integral is natural log of x plus c, but there is 5 over x. But in chapter 4 you saw that if there is a number, a constant, you can pull that out, right? So you can write 5 and the integral of 1 over x dx, right? So what will be the final answer? Now you use that formula. So 1 over x dx is natural log of x plus c. 5 is already there, so like 5 natural log of x plus c. You see that? So if there is a number, you can pull that outside the integral and then find the integral of 1 over x only, so that which is natural log of x plus c. Actually this 5 you could multiply with c and then write 5c, but c is just a constant, so 5c is also another c. That's why this is the final answer. Now on this, by the way, let me tell you one thing. What is the derivative of x? What is the derivative of x? Derivative of x is 1, right? So from here you can see that if there is something in the denominator whose derivative is in the numerator, okay, if there is something in the denominator whose derivative is in the numerator, then the answer, then the integral is natural log of the denominator function. You see that? We could see from this, okay, from this formula or from this example as well, but I'm giving you one more example that verify that, okay, and then I will develop that as a formula. Okay, so let us look at this. How do I find out the integral of this? Because I want to write in terms of the log, but log needs x in the denominator and 1 in the numerator. But how do I do that? So you remember from chapter 4 from calculus 1, the substitution method, right? So what I'm going to do is I'm going to do 2x minus 1 equals to u. Set 2x minus 1 equals to u. Now find out the derivative. What is the derivative of 2x minus 1 if you find out with respect to x? So the 2 equals to du over dx, right? So you can write 2 dx is equals to du. You see that here? So you will replace this 2 and dx by du, and then 2x minus 1 by u, right? So this integral can be written as 1 over u times du, because in terms of for 2 and dx I'm replacing by du, and then 2x minus 1 is u, right? So 1 over u times du. So what is that? That will be basically natural log of u plus c, right? You see that? Because of that formula, if you have 1 over x dx, you see that this matches, right? Did you see that this matches with that x? So here also u matches with du here, right? So in that case you can write natural log of the denominator function, natural log of the x plus c, natural log of denominator function plus c. But your question was in terms of x, so you want to plug in back, you want to substitute back. So u is 2x minus 1. So for your final answer is natural log of 2x minus 1 inside the absolute value plus c. That is the final answer. Okay, so if you want to do it directly, what do you find here? What is the derivative of 2x minus 1? It is 2, right? Because the derivative of 2x is 2, and the derivative of 1 is 0. So the derivative of 2x minus 1 is 2. You see that? Since the denominator function has a derivative on the numerator, so the final answer is natural log of the denominator function. That's what we got here. You see that? That's the same thing happened on this formula as well. The derivative of x is 1. That's why the integral of 1 over x is natural log of the denominator function plus c. Here, the denominator function is 2x minus 1. The derivative of 2x minus 1 is 2, which is in the numerator. So a function is in the denominator and its derivative is in the numerator. So the integral of this composition, right, this combination is basically natural log of the denominator function inside the absolute value plus c. That's what I see that. I mentioned that here. Thus, we see that if you have integral of a function in the denominator whose derivative is in the numerator and then dx, this u is function of x and u prime will be function of x as constant, okay? You see that a function and its derivative on the top dx, then the answer is natural log of, then the integral is natural log of u plus c. Now look at this here. Do you see that? What is the derivative of x squared? Is 2x, right? Which is in the numerator. You see that? So what will be the integral here? That will be basically natural log of x squared minus 4 plus c. Okay? So you can directly write down that way. If there is a function in the numerator whose derivative is in if there is a function in the denominator whose derivative is in the numerator, that's all, there is nothing else, then you can write the whole integral as natural log of the denominator function plus c. Okay, now let us see here. What is in the denominator? There is 1 minus x cubed. Okay, what is the derivative of 1 minus x cubed? So the derivative of 1 minus x cubed will be negative 3x squared. That's what the derivative of the denominator function. But we don't have negative 3x squared here. If there was negative 3x squared, then you would be able to write the integral is equals to natural log of the denominator function. But there is just x squared. But since this is since there is just a constant missing for the derivative, so what you can write here is this can be written as, you can write 1 over negative 1 over 3, and then you can write negative 3x squared over 1 minus x cubed. You can write that way, right? You see that? And then dx. Now there is a function in the denominator whose derivative is exactly the numerator. So sometimes if the derivative is not exactly what it is in the numerator, then you can multiply by a constant or divide by a constant and make it the derivative of the denominator function and then use that formula, right? So negative 1/3 is negative 1/3. Now this integral is basically natural log of 1 minus x cubed, and then that is the absolute value, and then plus c. That's what you can write. Okay, so that is the final answer. But you know, if the numerator is missing some x to become the derivative of the denominator function, you cannot do 1 over x and then outside and then x, because that is a function of x. You cannot write down that. You cannot write that down. Okay, if it is off by a constant, then you can multiply by a constant or divide by a constant to make the derivative, or add constant and subtract constant like that. Okay, you can do that way. All right, so that is another example using where the answer is the log function. We're using the same technique here. Okay, so if there is a function in the denominator inside the integral whose derivative is in the numerator, then the integral value is natural log of the denominator function. Okay, now what do you think the integral of sine x is? So you have to look at on the you may have seen that already, but we need to look at the derivative formula. Okay, look at this. So the derivative is and the derivative and antiderivative are the inverse process, right? So if the derivative is, so look at this, if you take the integral here, you will get the integral of d over derivative of sine x is equals to cosine x, right? Since the derivative of sine x is cosine x, so the integral of cosine x will be sine x, right? Similarly, what is the derivative of cosine x? Is negative sine x. So what will be the integral of negative sine x? The integral of negative sine x will be cosine x, right? But integral of positive sine x will be negative cosine x. Negative cosine of x plus c. That's what you get. Okay? Similarly, what will be the integral of cosine x? Since the derivative of sine x is cosine x, right? You see that? The derivative of sine x is cosine x. Since the derivative of sine x is cosine x, so the integral of cosine x will be just sine x, right? So it will be basically sine x plus c. Now look at this. What is the integral of cotangent x? So do you know what is the derivative of what is the function whose derivative of cotangent x? I don't know. So what I'm going to do is I'm going to write this in terms of sine and cosine. So cotangent is ratio of cosine of x over sine of x dx. Now, can you use that log idea? Because there is a function in the denominator whose derivative is in the numerator, because the derivative of sine x is cosine x, right? If there is a function in the denominator whose derivative is in the numerator, then the integral is natural log of denominator function plus c. Here, that's the same thing. So you write natural log of sine x absolute value plus c. That's all. How about the tangent x? Do the same thing. Sine x over cosine of x dx. What is the derivative of cosine x? That is negative sine x, right? The derivative of cosine x is negative sine x. So we are basically short of negative sign here. So you can write negative and then negative sine x. That will make it positive, right? Over cosine of x, because we have positive here, so negative times negative will be positive. But we wrote negative sign inside because the derivative of cosine x is negative sine x dx. So you can write basically negative of natural log of basically this is cosine of x plus c, right? And some people, you know what they do is they move this negative sign on that and then write cosine x to the negative 1. And you can write cosine x to the negative 1 as 1 over cosine x, right? You can write natural log of 1 over cosine x. 1 over cosine x is secant x plus c. So some people use this format as the antiderivative of tangent x is natural log of secant x plus c, that way. Okay? So we know the antiderivative or the integral of sine x is negative cosine x plus c. That's the formula, okay? The integral of cosine x is sine x plus c. Integral of cotangent x is natural log of sine x plus c. Integral of tangent x is natural log of secant x plus c. Okay, now what is the integral of secant x? So it is a little bit different, okay? Integral of secant x, we don't know a function whose derivative is secant x. That's why we need to do slightly differently. How do I do that? Is secant x, I am multiplying and dividing by secant and tangent, okay? I'm doing secant x plus tangent x. I'm multiplying and dividing by that function. Secant x plus tangent x dx. So how did I write that? Because I knew that this is a tricky thing, okay? Some of the tricky thing you need to memorize, all right? So because I knew that the derivative of the denominator function will be the numerator function, okay? Why? Because look at this. So how can you write this one? You can write this one as, if you distribute this, you write secant square x plus secant x times tangent x, okay? And then over, can I write tangent x plus secant x? You can write that because this is plus, right? You can write this plus this or this plus this, not a problem. So tangent x plus secant x. Why did I do that? You will see dx. Now look at this. What is the derivative of tangent x? Secant square x. What is the derivative of secant x? Secant x times tangent x. Here, the derivative of the denominator function is the numerator function. The derivative of denominator function is numerator function here. So what is the final answer then? It will be natural log of secant x plus tangent x, or you can write tangent x plus secant x, okay? Secant x plus tangent x, absolute value plus c. That is the final answer. So this was a little bit tricky. This is the formula for integral of secant x, or antiderivative of secant x is natural log of secant x plus tangent x plus c. So similar trick will be used for cosecant x, okay? So this will be integral of, you can write cosecant x, or people also write CSC, okay? Instead of cosecant, people also write CSC only, and book also use just CSC, okay? CSCX. What I'm going to do is I'm multiplying and divide by cosecant CSCX minus cotangent x, and then divide by CSCX minus COTX. I'm dividing and multiply by the same thing. So if you cancel out, then you will get cosecant x only, right? It's the same thing as before. If you cancel them, if you divide them, you'll cancel and it become 1, so which is same as the previous one. I'm just dividing and multiply by the same thing, so you can keep the equal to sign, okay? Now if you distribute this, what do you get? If you distribute this, you will get integral cosecant square s minus cosecant x times cotangent x, okay, and divide by cosecant x. So you can write this as, I can write negative cotangent x and positive cosecant x. Why did I do that? Because the derivative of negative cotangent x is cosecant square x, or you can say derivative of cotangent x is negative cosecant square x. You can see it here, right? We have the formula table here. You see that the derivative of cotangent x is negative cosecant square x, or if you move that negative sign here, you can write derivative of negative cotangent x is positive cosecant square x. That's what it is happening here, right? And what is the derivative of cosecant x? The derivative of cosecant x is negative cosecant x times cotangent x. Negative cosecant x times cotangent x, right? So what is the final answer here then? So here also the derivative of the denominator function is the numerator function. So you can write natural log of cosecant x CSCX minus cotangent x plus c. When I write the final answer, I can write this one first and this one second. Either way, it is not a problem, right? Because I am keeping the same sign. See, cotangent has negative sign, cosecant has positive sign. You can write this forward, this backward, it's the same thing. I was just moving them in this way just to show you that this one has derivative that, this one has derivative that. And then the whole thing in the denominator has derivative in the numerator. That's why you can use that technique, meaning the natural log of the denominator function with the absolute value and then plus c. Now you see that we found the integral of all four functions. This is formula number 1, formula number 2, formula number 3, formula number 4, formula number 5, and then formula number 6, right? So we learned how to find out the integral of the 6 trig functions, okay? And also we learned another formula here, which is if there is a function whose in the denominator whose derivative is in the numerator, then the integral will be natural log of the denominator function plus c. That's what we learned. Okay guys, so in the next video I will show you more examples from the book on how to find out the integral of many other functions using these techniques that we learned in this video. Okay guys, thank you.